we're talking about the strength of the riveted joint. So we will continue from the place where we left in the previous class. That is the strength of the type of failures of, and the rivet is getting shared at this critical location. This is the sharing failure, and the second one is, you can see that the critical cross section of the plate is minimum at this point. So this plate is going to fail under the tensile failure, is this part. And the third one is the tensile failure between the next one is the crushing failure. This is the crushing failure of the plate by the rivet, because this rivet is kind of crushing into it. And the fourth one is the shear failure of the plate, because the plate is shearing in this manner. So it is the shear failure. Here it is the shear failure of the rivet, whereas this is the shear failure of the plate. And then the last type is the tearing of the margin. Since the margin is too close here, this would kind of tear it. So this is the tearing failure. Of margin. These are the typical kind of things that generally people see in terms of failures in the riveted joint. Important is the kind of shear failure, tensile failure, and the crushing shear failures are the important. So we will kind of note down what are the typical formulas that we need to use to determine the strength in these three failure criteria. The first one is the shearing failure. For that we need to know the shear strength of the rivet. The shear strength of the rivet, PS, is given by the area of the thing is pi by 4 d square. D is the nominal diameter of the rivet, times the shear stress tau will give you the shear resistance of the rivet per pitch in the unit direction. So where d is the diameter of the shank, and tau is the permissible shear stress of the rivet. Now this is for the general one shear, but there are several kind of failures. For example, you can have shear failures which because of double shear, triple shear, or you can have double strap, as we have seen in the previous class. So based on that, you can have different types of failures, shear failures. So let me show you that. So in this case, first case, this is a single shear, a single rivet. It is under single shear. So in this case, the strength is given by pi by 4 d square into tau. Whereas there can be scenarios. So this one is, there is one shearing and another shearing. So this is a double shear, and since you have strap on this side and the other side, this is double strap failure. So in this case, PS is equals to pi by 4 d square tau into n, where n is equals to 2, because this is undergoing the double shear. So for multiple cases, you'll have multiple stuff. That is the thing. But further, so you have two such kind of things. This is first rivet and second rivet. This has to be multiplied by 2. So in this case, it is 2 tau into n, and n determines type of shear. So this is the shear stress. The second one is the tensile strength of the plate. As we have seen earlier, in this case, you can see if I take a length of the plate between this to this, we can see that, or you can even take it from this center of the pitch to the other center of the pitch. We can write the net resisting cross section as P minus D. You can write it actually as P minus D by 2 from one side and another D by 2 from another side times H, or the thickness T, that is given as P minus D into T. So the tensile strength of the plate is given as, this is the small p pitch, where small p is the pitch of the rivets and T is the thickness of the plate. And sigma T is the permissible tensile strength of the plate material. So that is the second kind of failure. The third one is, the third most important is the crushing failure. The crushing failure is the thing. This is the crushing failure of the kind of a plate. In this case, the projected area of the rivet on the plate A is equals to D times T, and hence your P crushing is equals to D times thickness times sigma crushing. And if there are multiple rivets, then you will have an N, which determines the number of rivets that is facing. So D is the diameter of the shank, T is the thickness of the plate, sigma C is the permissible compressive stress of the plate. So further, there is something called as efficiency of the joint. So it is defined as lowest of PS, PT, PC divided by capital P, where capital P is given as pitch times thickness times sigma t. So this is defined as the efficiency. So, and when people are designing, people will take directly for things the P for designing is simply taken as efficiency times capital P, and this will be used so that it can avoid both the shear tension as well as the crushing failures of the riveted joint. So these are the kind of basic equations that are used at later point of time in studying the design of the riveted joint. The next thing is caulking and fullering. So these processes are used to obtain leak-proof riveted joints, because most of the time they are used in pressure vessels. In the pressure vessels, it is mandatory to kind of have a leak-proof conditions. So in order to attain such kind of a leak-proof things, under the maintenance, one has to go either do caulking or fullering. Let us say what is the kind of caulking. So caulking is done in this manner. There is this caulking tools, and either you put it here at the head or at the edge of this plate, and then you just hammer it. By doing this, it will kind of close the cracks between these metal surfaces, and that's how they try to prevent the leak. So caulking process is applied to the edges of strap plates in a lap joint and the edges so the strap plate is in butt joint, and edges of lap joints these edges are first beveled to approximately 70 to 75 degrees, So can you see? So these edges, right? These edges are 75 to 70 degrees. So, and over that your tool is cocking to either by hand hammer or by the use of pneumatic or hydraulic hammer. The blows of caulking tool closes the surface asperities and cracks on the contacting surfaces between two plates and also between and the plates, resulting in leak proof. Further, caulking should not be done for plates less than 6 mm thickness. Next, fullering. This is similar to caulking, except the shape of the tool is flat or blunt as compared to caulking tool. So let us show that picture. So here it is kind of a blunt tool, whereas in this case it is a sharp tool. So now let us take some examples. So let us try to solve an example using the strength. So let us solve this one. Consider a brake band attached to the hinge of a riveted joint as shown in figure. We need to determine the size of the rivets needed for the load of 10 kilonewton, and also determine the width of the band when the permissible stresses for the band and rivets in tension, shear, and compression are 80, 60, and 120 Newton per mm square, respectively. Let us assume M is equals to 1.5 times T, and pitch T is equals to same as in the longitudinal direction. The band can be determined. So we know that the total load is 10 kilonewtons. The thickness of the plate, as shown in the picture, is 3 mm. Is 80 MPa. Tau is equals to 60 MPa. Sigma C is 120 MPa. So since these rivets are under the double shear, you can see they get sheared at this place and this place. And there are two such rivets. So let us assume here, and then fullering. Then we started doing this example, and this is we have a single shear here, and there are 4 such rivets. So if we consider shear failure, we can write this one, and based on the diameter is this guy. Now similarly, based on the crushing or other criterias, we can show that for crushing, for D, T is the projection area of the 4 things. Sigma C is equals to 10 kilonewtons. So 4 into D into 3, and crushing is 120, and that implies D is equals to 6.94. So this is also kind of fine for us because we are applying 8 mm. So we will take it as 8 mm. So that means now we can determine the width of the plate is W minus 2D times into 3 into 80 is equals to 10 into 10 power 3. That implies W is equals to minimum of 57.67. So we will take 60 mm. So then we can decide our pitch of the rivets as, since we know M is equals to 1.5 times D, that is equals to 1.5 times of 8, that is 12 minimum. We can give approximate to 15 mm. Then P plus 2M will give us the width, that is pitch plus 2 into 15 is equals to 60, or the pitch is equals to 30. Since we assumed P transverse is same as P, then this is also 30 mm. So this means in this case this distance is 30, this distance is also 30, this is 15, this is 15, 15, 30, 15. So this to this is W. So hence we defined that is same as this W. So we have determined the width of the things. That is how this plate is kind of designed for the riveted joint. So next example, since we have lost time, the next thing what I will do is we will try to solve the problem for the longitudinal butt joint for the boiler shells, because mostly these are used for the boiler shells. So let us study the next one is longitudinal butt joint for boiler shells. Let us see how they look like. So this is a kind of a boiler shell where you are doing a butt joint. That means you can see this is one plate and this is another plate. They are kind of ending at this plate, and you are putting a strap inside. This is the inside strap, and there is an outside strap, that is this. So after having the inside and outer things, you will get such kind of a longitudinal butt joint. So in these cases, these are generally used for designing boilers. So we need to understand few important things for designing of these things. Those are thickness of the boiler shell, first one. The thickness of the boiler shell is given as pi di divided by 2 sigma t, where pi is internal pressure, di is internal dia of the cylinder, then sigma t is permissible tensile stress of the cylinder, and T is the thickness T is the thickness of the boiler shell. So sometimes, since these are used for the applications of boilers, they are generally also used with certain efficiency. So in those cases, we modify the above formula by dividing it with an efficiency, and this is eta is the efficiency of the riveted joint. So this is for the thickness of the things, and in order to, since these are at high, are exposed to harsh environment, they are also subjected to corrosion. So one has to also allow for the allowance for the corrosion allowance CA to metal thickness to resist internal pressure. So that is given as T is equals to pi di 2 sigma T with an efficiency plus your CA is there. Your CA is a kind of different kind of what do you call it as corrosion allowance. The efficiencies as well as the kind of these things has certain guidelines to be followed, which we will kind of give you. So for example, if you want to take efficiencies, the efficiencies are depending upon the type of the joint. So for a kind of lap joint, single riveted, people take it from somewhere in between 0.45 to 0.6, whereas a double strap butt joint, which is triple riveted, can be taken as 0.8 to 0.9. So these are the things that is there, and based on the corrosion allowances, this thickness kind of in this formula, you add a certain more thickness compared to what it resists the internal pressure. This is one thing. The second thing is the tensile stress that is permissible in the cylindrical material. So sigma T is generally obtained as SUT divided by factor of safety, and in general there are specific grades that, and in those cases those can be represented as okay, let me just give it to you. The boiler grade materials are ST37BR, whose SUT in terms of Newton per mm square is given somewhere between 360 to 400 Newton per mm square, sometimes up to 440 Newton per mm square. Then ST42BR grade has a SUT ranging from 410 to 500 Newton per mm square. So this sigma T is obtained depending upon the type of the grade used in this materials, and based on that one can really decide what is the minimum thickness of the shell, cylindrical shell for the boiler shell it is required. So this is the one, and when you're deciding the diameter of the rivet, we generally follow Indian boiler regulation, and according to that, when T is greater than 8 mm, then diameter is equals to 6 root T, and this is called Irwin's formula. And when the T is less than 8 mm, then D is obtained using shear resistance. Of the rivet. And in any case, it should also follow the excuse me, minimum diameter requirements for the different thicknesses. So D cannot be less than, or D has to be greater than this thing, and this is the diameter of the rivet, but the diameter of the hole and the diameter of the rivet has certain criteria that has to be met. Those are tabulated here, which will give it to you. So hole dia is D dash is hole dia, D is shank dia, or simply rivet diameter. So the relation should be these things. So you need to give a little bit clearance for those things. The clearance is given in this manner. So if it is 12, you give 13, and if it is, let's say, 36, you give 37.5, and so on, like this. So this is the kind of these are all Indian boiler regulation. And further, the pitch has certain criteria. When it comes to pitch, the pitch in the middle and inner rows is 1/2 of the pitch in the outer row, and generally the pitch requirement is obtained by equating it to the shear strength of the rivets. So as we already have calculated the shear strength in the previous example, we'll use it. Okay, and we can as well as calculate the once we know the pitch, we can also calculate the tensile strength of the plate. And this is how one would kind of in times thickness. So is the tensile strength is kind of determined. And let's say when people are considering the shear resistance to find out the pitch, then we need to assume shear resistance for single shear. The PS is equals to pi by 4 d square tau for single. If you have multiple rivets, you just multiply with the number of rivets. But when it comes for the double shear, PS is equals to pi by 4 d square tau times 1.85. This is not give less factor, that is 1.875. So this is kind of things. So if there are a couple of mixed things, let's say generally we have let's say n1 number of rivets under and n2 number of rivets under double shear, then your total PS is equals to pi by 4 d square tau into n1 plus pi by 4 d square tau 1.85 into n2. So this is can be simply modified as or the pitch can be obtained from this side as if tensile strength of the plate is same as shear resistance, then P minus T times thickness into sigma T is equals to PS, right? So in that case, you can directly equate and get your pitch as N1 plus 1.85 N2 pi d square T divided by 4T sigma T plus T. Further, there are certain minimum criteria has to be written. So further, P minimum has to be at least 2D and P maximum has to be C times thickness plus 41.28, where the values of C can be given as these are the values of the C for different type of the joints. And if you know the thickness and if you know the C value for a given type of the joint, you add these things and you get P minimum and P maximum. So you need to make sure your pitch lies between both the things. And when it comes for the transverse pitch, the transverse pitch is decided as 33% of P plus P, or this is for the zigzag riveting, and this would be 2 times of T for chain riveting, that is which follows one single line, and the margin so before we go to the margin, there are minimum pitch. So minimum distance PT between outer and inner row has to maintain 0.2 P plus 1.15 D for zigzag as per the Indian boiler regulations, and minimum distance between the rows has to be 0.16 P plus 0.67 D. These are minimum requirements. You can have greater than that, it should not be a problem. And at the margin between the end of the plate and the first row, so margin M is given as 1.15 D, and the thickness of the straps the T1, which is the white strap that is inside, T1 is minimum of 0.75 times T, and for a narrow strap so then there are certain limits on the permissible stresses. On permissible stresses are SUT has to be 26 tons per unit or per square inch, and SUS is 21 tons per square inch. That comes out 1.27 Newton per mm square in SI unit. This comes out to be 324.11 Newton per mm square. and generally a factor of safety in this cases of an order of 5 is applied, then your permissible sigma t would become 401.27 by 5 equals to 80.25, and shear stress tau is given by 324.11 is 64.82 Newton per mm square, and under sigma c is taken as 1.5 times sigma t, so that would come out to be 120.38 Newton per mm square. So given these things, one can clearly design a kind of butt joint for the cylindrical shells, cylindrical boiler shells. So this is the kind of things we can look at an example. For example, a cylindrical shell with let's say the internal pressure is 1.5 MPa, and the efficiency of the joint is 80%. The internal diameter is 1.5 meters, and sigma c is equals to 120 Newton per mm square, and tau is 60 Newton per mm square, and sigma t is equals to 80 Newton per mm square. We need to design this kind of a butt joint for the cylindrical shell as shown in the figure. This thing, so first thing is let us decide the thickness of the shell. T is given as pi di divided by 2 sigma t efficiency plus corrosion thing, which is given as 1.5 in terms of MPa, 1500 divided by 2 divided by 80 divided by 0.8. Let us give corrosion as 2 mm. So that will give you 19.58, which will approximate to 20 mm. So now, second step, diameter of the rivet. So since T is greater than 8 mm, because we got 20 mm, so based on that, we decide D is equals to 6 root T, that is equals to 60 root 20, that is equals to 26.83, will approximate to 27 mm diameter of the rivet will be used. Next is the pitch. Pitch of rivets. So we take pitch is equals to N1 plus 1.875 N2 by d square tau divided by 4t sigma 1 sigma t plus dia. So for this case, as per the picture, we can see that we have to work out on different combinations. Let us assume our single share is 0 and double share are in phi. In that cases, we will get our pitch as 228.29, which can be approximated to 230 mm, but we need to stick with the minimum and maximum P min. So P minimum is equals to 2 times D, that is equals to 2 times 27, that is equals to 54 mm. This was fine. And P max has to be C times T plus 41.28, that is equals to, in this case, our C is 6, this is 20 plus 28. So it turns out to be the pitch is 161.28. So, but you cannot use 230. So P is greater than P max, and hence a pitch of 160 mm is used. And then for the transverse pitch, PT, we'll use 0.2P plus 1.15 D, that happens to be 63.05 approximated to 65 mm. This is for the outer and middle rows. This is the between outer and middle, and for the middle and in 0.67 D formula will be used. This will give 44.49 for inner and middle is used, is the pitch. And for the margin, we'll take M is equals to 1.5 times D, 1.5 times 27 is 40.5, so approximate to 45 mm. Then comes is the thickness of the straps. So T1 is 0.625 T P minus D by P minus 2D formula. That will give us 15.68 approximated to 16 mm. And efficiency of the joint P is given minus P minus D times T times sigma T, that in this case is 212.8 kilonewton, right? Similarly, PS is obtained as N1 plus 1.87 into pi by 4 d square tau is obtained as 322.06 kilonewtons, and Pc is n1 plus 324.0 kilonewtons. So, and capital P is equals to dt sigma t, that is equals to 256.0 kilonewtons. So the efficiency is minimum of Pt, Ps, Pc divided by P happens out to be, in our case, 0.8313 or 83.1 percentage. So in this case, this is what is our case, which we have decided based on the things. Our pitch was 160, and we have shown that from the outer to inner is 65, the inner to in between is 45. The things, the thickness of the straps are 16 mm, and the thickness of the shell is 20, and this is the kind of arrangement which we have solved today. So this is the part of the eccentric shells with respect to so this is the kind of butt joint for the cylindrical shells. The next last topic today which we'll deal would be on the eccentrically loaded riveted joints. So in this case, we have two things. So the eccentricity is in the plane of the rivets. So it would look something like this. That gives you the primary forces, primary shear forces. So which we'll call it as P1 dash, P2 dash, P3 dash, P4 dash, since there are 4 such kind of things, which is given as all are equal to the total load P divided by number of rivets. So in this case, since we have 4 rivets, this is P is 25 and number of rivets is 4. Okay, then comes secondary shear force. The secondary shear force, which will give as P1 double dash, P2 double dash, P3 double dash, and P4 double dash. So all are proportional to kind of distance from the CG. So this is the center of gravity. The secondary shear stress would be proportional to how far they are there from their corresponding CG. So we can write this one as accordingly. C times R1 and P2 dash is equal to C times R2, P3 dash C times R3, P4 dash is equals to C times R4. This secondary shear would balance secondary shear balances the moment, hence that is P into R1 plus P1 double dash R1, P2 double dash R2, P3 double dash R3, P4 double dash R4 has to be equal to M, where M is P times E. So based on this and these things, we can say our C is given as P into E divided by R1 square plus R2 square plus R3 square plus R4 square. So in our case, so now once you know this C, you put it back in this place, you will get back your answer. So P1 dash double dash is P E R1 divided by R1 square plus R2 square plus R3 square plus R4 square. Accordingly, the other things can be done. So let us quickly solve this problem which we have seen and then determine the solution before we end today's class. Okay, so this is the problem. So our capital P in this case is 25 kilonewtons. Number of rivets are 4. So P1 dash, P2 dash, P3 dash, P4 dash. Primary shear force are given by P divided by N, that is 25 divided by 4, that is equals to 625. This is kilonewton, newtons. So second is secondary shear. So the secondary shear, we know that our C is given by P into E divided by R1 square plus R4 square. So in our case, E here, in this case, from the CG, which is, this is the line passing through CG, is 25, and from the CG, R1 is 150, R2 is 50, R3 is again minus 50, R4 is on the 150. So you can write E is 100, R1 is 150 mm, R2 is 50 mm, R3 is 50 mm, R4 is 150 mm. So based on that, if you just put it back, C can be written as 25 10 power 3 into 100 divided by 150 whole square plus 50 whole square plus 50 whole square plus 150 whole square. This happens to be 50, and hence, so P1 double dash is equals to C times R1, that is equals to 50 into 150, that is equals to 7500 newtons. This is Newton per mm, and P2 is equals to C times R2, that is 50 into 50, that is and P4 is C times R4, that is again 7500 newtons. P3 is C times R3, that is 2500 newtons. So the resultant P1 is P1 square dash plus P1 double square under root square root. So that would be given as 6250 cell, the highest will be P1 or P4. So we can just 00 whole square. That will give us as 9762.81 newtons. So dia of the rivet is P1 is equals to pi by 4 d square tau, and that implies 9762.81 is equals to pi by 4 d square 60, because tau is 60, d comes out to be 14.39 or 15 mm. So with this we have finished which we have finished the problems on the riveted joint. In the next class I will start on the bolted joint, which is much more similar to this, and we will also try to cover the shafts in the next class. So with this I'm going to end the class, but I would have another request. Can I